Just for the sake of completeness, I'm going to go over Cartesian products again because the recording of the last lecture got cut off. The battery died on my recording device. So it's not on the YouTube video. So I wanted to make sure it was included for future reference. So we're going to redo Cartesian products and move on to sets and relations and functions and graphs. Cartesian products you have two sets, say A and B. A, say, is equal to 1, 2, 1 and 2, and B is X, Y, and Z. The Cartesian product of that, with the notation of A, B, A large X, B, generates a set of ordered pairs, or ordered triples if it's a cross product or a Cartesian product of 3 sets. You take every combination of A and B with the A elements in the first spot in the ordered pair and B elements in the second spot in the ordered pair. So the cross product would be a set 1, X, 1, Y, 1, Z, 2, X, 2, Y, and 2, Z. So the number of elements in the set of the Cartesian product is the number of elements in A times the number of elements in B. So number of elements equals number in A times the number in B. So we have 2 times 3 is 6. So we have 1, 2, 3, 4, 5, 6 elements in the Cartesian product. Just to note that the order on the ordered pairs matters. This is not the same as X, 1, like in set notation. The ordered pair with the parentheses, order matters. 1, X is different from X, 1 in an ordered pair. It's kind of similar to an array in C++, where the order of the elements does matter, just with different notation. Now, let's see here. That's about it for the Cartesian products. That's the basics of them. Now, where Cartesian products come into play is in the area of relations and functions. A relation, say, let's see here, what's the example that they give here? Okay, let A be equal to 1 and 2, and B equal to 1, 2, and 3. Okay. Define the relation R. How does it word it here? Given any x comma y being an element of R means x minus y over 2 is an integer. Okay. First, what are the ordered pairs in a Cartesian product with B? So it'd be, I'm not going to write them all out, but 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. Okay, so you'd first find a Cartesian product with B. Then you determine which of those ordered pairs satisfy the condition here. All right. So let's go to a clean play page here. Well, I guess I better do it. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3. Okay, so there's the Cartesian product of A and B. Okay. Now, which ones of those satisfy the condition of x minus y equals over 2 equals an integer? That would be 1 minus 1 over 2 equals 0 over 2, which is 0. There you go. This one would be 1 minus 2 over 2 equals 1 over 2, or minus 1 over 2, which is not in the relation. 1 minus 3 equals minus 2 over 2 equals minus 1, which is an integer. do these in your head here. 2 minus 1 over 2, 1/2, so that's not. 2 minus 2 over 2, 0. So it falls in the relation. And so 2 minus 3 over 2 would be negative 1/2. So that would not be in the relation. So the relation, notated as A, R, B, would include 1 comma 1, 1 comma 3, and 2 comma 2. Now, a little bit of terminology. For a relation, this is the domain, A, the first one, and B is the codomain. Not the elements that are in, it's all the elements in those sets, not the first numbers and the second numbers. It's the entire sets. In this case, it is the entire sets, but sometimes a relation will not have all the elements of the domain and codomain. All right. Let's see here. One way to represent this is in the area of with a arrow diagram, and we're going to erase some of this stuff, stuff that we don't need. Okay, so we have the A is related to B with this set. So to draw an arrow diagram of this, you draw the domain on the right, or left, sorry, 1 and 2. 1, 2, 3, the codomain on the right. And then you would draw arrows from the elements in the domain to the elements in the codomain that make up the ordered pairs in the set that satisfies the relation. So that is how the arrow diagram would be for A is related to B. Okay? Now, a function is a relation. Let me let you catch up with the drawings and all that sort of thing. I see people still jotting stuff down. Okay. All right. A function is a relation where, let's see here, where all elements of the domain are related to an element in the codomain. Okay. Now, what makes a function really different is that no two ordered pairs have the same first element. What this means is every element in the domain is related to an element in the codomain, but just one. Like in the previous example, we had one related to 1 and one related to 3. That would not be a function. It is just a relation. A function has all unique arrows coming from the elements of the domain. All right. Let's see here, and it's denoted by f of x. So let's give an example here. Let's see here. Let's do one with an arrow diagram. It makes it's the easiest to relate to. Let's see here. 2, 4, 6, and 1, 3, 5. 2, 4, 6, 1, 3, 5. And 2 goes to 5. And 4 goes to 1. And 6 goes to 1. Okay. This is a function. You notice not all elements of the codomain are referenced by the domain. That's okay. What's important is that all of the elements of the domain are related to some element in the codomain, but just one element. So if 2 were related to 2 and 3, or 5 and 3, that would no longer be a function. Okay, so let's take that out of there. So this is a function. Think of it a function like you have functions in C++. A function, just one second. A function in C++ returns a single value for each input that you give it. It doesn't return two values. They can't. It returns just one value. If it doesn't return a value, there's an error somewhere, making it not a function. You had a question? Okay. You can think of some people think of functions as little black boxes. Yeah. Yes. If there were say an arrow from 2 to 3 and 2 to 5, that would not make it a function. You would not be able to code that in C++ or any other language that I'm aware of. It's kind of like x. No. Let's see. Y equals the plus or minus the square root of x. That is not a function. Because it returns two values. The square root of 4 is either 2 or minus 2. You have to specify whether or not you want the negative square root or the positive square root. So, not a function. Any other questions about functions? I mean, you've been programming, I'm assuming you've all been programming a little while in C++, so you understand the basic idea of functions? Pretty much? Yes? No? Yeah? Somewhat? Okay, well, this is mathematically defining what a function is. Every element of the domain has one and only one element in the codomain related to it. All right. Then we move on to graphs. This is the last section of chapter 1. Graphs contain a set of vertices and edges. So it's defined by two sets. A edge it connects two vertices. So an edge can be straight, curved, or and should either connect one vertex to another or a vertex to itself. So see here, this example graph here. Okay, you got 4 vertices here. And edge 1, edge 2, edge 3, edge 4, edge 5. Okay. Okay. And then we got a V 5 out here. Okay. Vertices are labeled with V's. V1, V2, V3, V4, V5. Edges are labeled with the E, and you have a line, and they connect vertices. E1, E2, E3, E4, E5, and nothing over by V5. When you have 2 edges connecting the same 2 vertices, they are said to be parallel, though whether they're curved or straight, how they're drawn is irrelevant. Because they connect the 2 same points, they are considered parallel. So when a vertex is connected to itself, the edge is called a loop. E5 is a loop. E2 and E3 are parallel. And then V5 is said to be isolated. Okay, I'm going to go ahead and read this definition. A graph consists of 2 finite sets of a non-empty set of V of vertices and a set E of edges, where each edge is associated with a set consisting of either 1 or 2 vertices called its endpoints. The correspondence from edges to endpoints is called the edge-endpoint function. An edge with just one endpoint is called a loop. 2 or more distinct edges with the same set of endpoints are said to be parallel. An edge is said to connect its endpoints. 2 vertices that are connected by an edge are called adjacent. So we'll say V1 and V4 are adjacent. And a vertex that is the endpoint of a loop is called adjacent to itself. So V4 is adjacent to itself. An edge is said to be incident on each of its endpoints. And 2 edges incident on the same endpoint are called adjacent. So E1 and E4 are adjacent edges. E1 and E4, because they share an endpoint, V4, those edges are adjacent. A A vertex with, on which no edges are incident is called isolated. Okay, now the endpoint table, edge endpoint function. You have, in this case here, you have E1, you have E2, E3, E4, and E5. E1 is, let me make sure I'm reading this correctly. Okay. Is the set of V1, V4. E2 is V2, V3. E3 is the same because it's parallel. And E4 is V3, V4. And E5 just has one vertex, so it's just V4. Yeah. So that's the edge endpoint function. All right. Now, a directed graph is a little bit different. Notice how the edge endpoint function here is a set. It doesn't matter what order, it could be V4, V1, it doesn't matter. Okay, but a directed graph let's go ahead and do a similar graph. The edges are arrows. V4, V2, V1, V3. A directed graph has arrows. So, you have the edge endpoint function. It's just E1, E2, E3, E4, and E5. We have E1, E2, E3, E4, E5. E1 is the ordered pair V1, comma, V4. It's an ordered pair with parentheses. rather than the curly braces. Okay? E2 is V3 to V2. And E3 is V2 to V3. So, because they are pointing in different directions, they are not parallel. The ordered pairs are different. E4 would be V3 to V4. And E5 would be V4, V4. So these two here are not the same because the arrows are going in different directions. Now, a little bit of terminology is the degree of a vertex equals the number of edges incident on it. So, how many edges are incident on V1? Just the one. On V1, it just has one edge on it. Okay, V4? 3. Because of the loop. Ooh, actually, loops are actually counted twice, so that would be 4. 1, 2, 3, 4. So loops are counted twice. V3, 3, would have a degree of 3, and V2 would have a degree of 2. Let's see here, where are we at? Oh, that brings us to the end of the chapter. What do you know? That's considerably faster than I was expecting. Any questions about this? We have 40 minutes, or half an hour or so left in class time. Any questions? I strongly advise asking them because Thursday you're going to have a quiz on Chapter 1. So the Chapter 1 slides, where I took all my notes from, are on in the files section of Canvas. So you can download those and see in more detail and more examples. Printed notes are acceptable on the quiz. No use of computers. It's a paper quiz. If you have notes on your computer, print them, bring those. But yeah, so questions about anything in Chapter 1? Yeah.
Like the edge endpoint, are those like in general? Like we can put those onto the sheet?
Yes, that's the edge endpoint function. Yeah, this is the edge endpoint function. So f of E1 would be the ordered pair V1, V4. So an ordered pair is a single item in the set So that does count as one item to be returned by the function. Kind of like returning an array or an object in C++. It is one item, but as far as being in the definition of a function, though one item might contain multiple values. So, any other questions with sets, with variables, relations, functions, graphs? No? Speak now or forever hold your peace. The videos will be uploaded to, this video will be uploaded this afternoon, so you can review anything you might have questions on. Yeah. Quiz on Thursday, and then we'll start on chat. The quiz hopefully won't take you the whole class period. We can start on chapter 2, which is the logic of compound statements. And we'll start on that on Thursday afternoon. Have a good afternoon, all.